Okay, STATIS, rather than dealing with one data set, let's say X, STATIS is dealing with several data set, X1, X2, XP. Okay, what can be this X that you see here? X can be, in our case, for instance, we are dealing with connectivity matrices. I am doing EEG and getting some data set, doing the reconstruction form, and then having any indices who merge connectivity. This one becomes the connectivity matrix. Okay. Oh, what is X2? Oh, I can do the same. Let's say I have I have one measure of connectivity. This is, I put it in X1. And my question is, oh, I have another measure of the connectivity. It can be correlation, or it can be PLV, or it can be synchrony, or it can be, so I put all of them together. Okay. Give X2, X2. And what is the question that I would like to ask? Is there any relationship between all the indices of the connectivity matrices? This is one question. What is the relationship between the different indices of connectivity in EEG? Okay, so I would like to see the comparison between the different matrices and extracting some features from that. Okay, so the method STATIS can respond to this. We can have other data set, let's say EEG. I have my sources over time, and I took the sources each, let's say, 2 seconds. So all what I have is data set in time, the sources, this is X1. Sources in window number 2, sources in window number 3, and so on, sources in window number P. So in this case, my question is there any relationship between the sources over time, knowing that, okay, windows means something for me. Let's say I took the window such as the signal is stationary. So maybe the signal is not stationary over time, but stationary in each time window. And I am asking about, okay, how the sources are going to behave depending on those time window. And this is more studying the dynamics of the sources over time, okay? So this is another question that I can address with this kind of technique. So I am going to give you very simple an example and showing you the steps of the method, which is really easy if you have in mind the PCA. It's a kind of generalization of PCA.
Just to clarify, you can use it, so you can use it alongside using different metric. I assume we can also using it multimodally, like in if one matrix is fMRI, the other is EEG, the other is diffusion MRI. Basically.
Sure. Yeah. All what you need is that to compare between the different matrices, you need at least one dimension where to compare between the different matrices. One dimension is what I call the individual. I put the start there. So it means that X1, X2 are measured over the individuals, and this is the same individuals who are repeated. So within the connectivity matrix, it's n by n, and the sources are the same, okay? But it can be like, I talk about time window. The time window, it's measured over the sources. The sources are the same, but the time window can be different. So let me just show you an example.
They should be independent, right?
No. No. It's your data set. This is input, okay? And independence is coming a bit later. Okay, and example, we have different experts 1, 2, 3. So I have 3 data sets, and they're just giving some like evaluation, grading different product. Okay, and they have their own like characteristics. This is data table X1. Okay, this is data table X2. As you can see, it's not the same number of variables. Okay, and this is a data table at X3. And the question is, okay, I would like to study those data tables. If I reduce the dimension and say, oh, I have only one expert, what you are doing is a PCA technique. You have data table X, okay, you move of what I mentioned, calculating the covariance matrix of this, and then getting the first, second, third component, and then analyzing your data set this way. Make sense? Okay. Okay, now I have this tree. So one question is, oh, is there any relationship between the expert? So this is more high dimension, looking at the data tables. And I would like to see if the products are graded the same way with the different experts. This is another question that I am going to ask, okay? So based on this, first thing that the STATIS method did is to just reduce the data set exactly the way that I have in mind calculating a covariance matrix. And the standard deviation gives you this kind of matrices. Okay, so I have 3 experts, 3 matrices, I reduce the 3 matrices. Okay, now, as I mentioned, you have to, I told you that X corresponds to an operator. The X that I mentioned here, I can associate to X a covariance matrix. Okay? So in my case, I have 3 covariance matrices because I have 3 data table X. Okay. So this is the covariance matrix coming from data table X1. This one is from data table X2 and so on. Okay, so 3 covariance matrices. Okay, and this is for the third covariance matrix. Okay, what we do with all of this? We met the compromise between the different covariance matrices. Let me explain this a little bit. So first, I took all the data set and I looked to the compromise. If you have data, usually you have in mind, what is the compromise in the data? Usually it's the mean of the data set that we have. Mean is usually the compromise. So what is the mean of covariance matrices? And this is exactly what we measure here. First, starting with the mean of covariance matrix. This is the generalization of the correlation between variables. The Hervé coefficient is exactly the correlation coefficient. But if the data set is a data table, so you can have something who generalize this correlation called Hervé coefficient. Okay, this comes from the statistics. I don't want to move more deeply, but this is simply to say, we can measure the Hervé coefficient, but Hervé coefficient comes from the different covariance matrices that I just calculate for each data table. Okay, easy. Mm-hmm. So the compromise is starting calculating this C matrix, which is a correlation matrix, but the matrix is in the dimension of the experts, the different covariance. Make sense for everyone? What is
just make a point there because we had the discussion earlier.
yeah
If we go back to your first matrix, it's very important. I want to clarify that you mean the data because to make sure it's covariance. I'm just mentioning that because we had the case in some of the Murray analysis here, like recently. So we have to be mean so that when we're gonna compute those matrices, we have covariance.
Okay, makes sense. Until now, I have data table. I go to the expert. I do some. I move with this RV coefficient, and this RV coefficient give me like a correlation between data tables. Okay, this is as a generalization of the correlation. Okay, so easy. If I have this correlation, okay, let's go ahead. It's like exactly here. I come with the covariance matrix. This one is the covariance. Look at the eigenvalues, eigenvectors of this compromise correlation matrix. And this is exactly what we do here. The notion in STATIS of compromise is looking at the RV coefficient between data table and doing a PCA. PCA on what? PCA on this compromise correlation. Very easy. It's not complicated at all. So in this case, this is exactly what the PCA did. We decompose the covariance matrix on eigenvalues and eigenvectors. Okay, so and the eigenvectors are of norm equal to 1. This is what I wrote here. Okay, and in this case, what is this? This is like a projectors. G is a projector on the eigenvectors of these compromise matrices. Okay. It's normalizing the component P, the eigenvectors of this component of this matrix. So in our example, P is this, the eigenvalues are those, and the normalization is this coefficient that you can see. Okay, so based on this, what we do with this? Okay, we do a representation. I have P. I have P1, P2, P3, and so on. Okay, let's go with P1 and P2. And so in this report is an expert. Okay, so a point becomes a data table. So I can represent in this between P1 and P2, I can represent the data tables. It's very interesting. So if you have a connectivity matrix between method 1, method 2, method 3, looking at the connectivity, for instance, the representation here is connectivity with correlation, connectivity with PLV, connectivity with etc. So this gives you like a representation which kind of connectivity are measuring the same kind of behavior on your data set and which one is quite different, giving you some information different from the other connectivity matrices. It can be also dynamic of over time. So if I represent the data table that, as I showed you, I told you about, I have different window over time, this one is going to give me the representation of all the behavior over time of the process that you have. Okay, so it can show you which time window is quite different, maybe at the beginning, maybe at the end of the process, and you have to deal, the interpretation is not there, but it gives you the similarity between the data matrices that you have on your data set. Makes sense at this stage? So I have data set, and I transform the data set same way as I do the PCA, calculating a kind of correlation matrices, and this is the compromise with the RV coefficient, moving to eigen decomposition of this, extracting the eigen decomposition, and now each data set is represented by a point, and I have now the representation between the different experts. Okay, that's it. That's very easy at this stage, but we can do more. Okay, what we can do? We calculate a covariance. Say you see that the first eigenvectors is almost the time positive in this kind of analysis. What does it mean? This is an eigenvectors who corresponds to the compromise between the different data, the different covariance matrices, how the covariance matrices are similar. It's like calculating a mean or a weighted mean. When you calculate a weighted mean, you have a weight, P1, P2, P3, and you calculate P1 by X1, P2 by X2, and you sum all those things. So you're calculating an average with weight. Okay, the weight here from the data set, because you are dealing, let's say, with PLV, and you are dealing with correlation. How you are going to weight the PLV and how you are going to weight the correlation. This is two things who are of different nature. So what STATIS tell you is the first eigenvectors of the compromise corresponds to the best weight from of your data set. So alpha 1, alpha 2, alpha 3, this is the coefficient alpha, are the weight and the best compromise weight. If I got the best compromise weight, I can then derive the best compromised mean. Mean of what? Mean of covariance matrices. And this is exactly what STATIS deal with. Normalizing the covariance matrices, coming with the weight that you got from the compromise. And this comes with this matrix here, 6 by 6 data matrix, which is the covariance matrix of the weight. So we can look at this compromise and try to interpret the compromise.
6 by 6. You have three
Yes,
here.
but you have 6 measurements.
You have 6 measurements. Okay, so you go
And
back to
you go back to
the
measurement, and you can come with the covariance matrices between the measurement.
So now you're back in the measurements, but weighted
By
the
the
information
compromise
from
of the STATIS method. Okay, so compromise of the STATIS method gives you the weight, gives you also the representation between the different tables. This is one thing of interest, but it's not enough. So that we have the weight, and if we come with the weight, we can just look at, okay, what kind of covariance matrices between the individuals that I have, I can extract from the data set. And this is the compromise within the individuals. And we can also look how best is the quality of this weighting. And this is something that we can calculate. It's easy to extract. If you remember, okay, let me just show you this. You remember that I move from the compromise, I derive the eigenvalues of this of the compromise, and the first eigenvalue is 2.7. Okay, now if I look to the compromise, it's 2.7 divided by 3, and what you can say is that you have 0.91 is the coefficient who is very close to 1, telling you that this compromise this is a kind of quality of the representation of the compromise regarding the data set that you have. When this coefficient is higher, it means that this compromise contains all the information that you have within the whole data set. Okay? So just keep this in mind, that when you would like to know about what is the how the compromise explain your data set, So you look at those kind of coefficients, it's easy to calculate. Okay. So based on this, I go ahead to the eigendecomposition of the covariance matrices of the compromise again. So step number 2, I got eigenvectors, eigenvalues, etc. So what I can do, I can represent the individuals, and the individuals is product 1, product 2, product 3, product 4, exactly as the PCA did. The PCA, you have a representation of variables and a representation of the individuals in 2 dimensions, okay? Representation of the variables I talk about. This is the representation between experts, first compromise. And within this compromise, you can have the representation of the different different individuals. And individuals is product 1, product 2, and you have the different products. What you can say is that those products are quite different from those products. So I have now in mind probably the type of the of those products. There is like a kind of classification within the product. So let's come back to the EEG and okay, what I have to represent here, it's the sources. And if I represent the sources, it's not the different method of connectivity that I am, the different method of connectivity. This is the step number 1. Okay. Step number 2 is, okay, within this compromise, how I can classify the sources, because in your data matrix, you have the sources. And you can have different type of representation of sources. This gives you networks. Okay, back to the networks. So because the classification of the different sources gives you the different network. So you have the different network that you are observing through the connectivity matrices that we are talking about. Make sense for everyone? Okay, so this is easy to implement. This is second step of the compromise at the level of the individuals, exactly like the spirit of the PCA technique. And so based on this, I can move to projecting all the study within the this compromise. What does it mean? I would like to see methods and individuals, product and expert. Okay, methods and sources within the same subspace. And within the same subspace, so what is the individuals here? Is the product 1 comes with the product 5, comes with the product 6 in one side, and you have product 2, 3, 4 in another side. Okay, we see also that how the I just represent this between this individual is I link it to the product 6. This individual, the same individual to the product 5, the same individual to the product 1. And one of the things that you can see is now is the expert that we have. We look at the relationship between the different expert and the different product that they are looking at. And one of the things who is interesting is even if those products are quite different from those products, we see like kind of discrepancy between this expert and those experts here. So which makes sense if you come back to the data set. This expert is not grading the product the same way, even if globally it's the same, but not exactly the same as this one and this one who are more related, okay, in their expertise. So we have this expertise that we can discriminate between the different expert and the product that they are looking at. So we do the same. We see that this expert is quite almost the time the guy who represent like the more bigger variance within this data set. So we see at this level. Okay, so what we have here is the fact that we have within the same representation, we have the representation of the expert and how those experts are related to the different product. Okay, so okay, let me come back to the connectivity matrices. We have different methods of calculating the connectivity, and this is the expert. And we have the different sources that we have, and all the different networks. So how the PLV discriminate between the different networks? How the correlation discriminates between the different networks? And probably the correlation doesn't have the same kind of discrimination or segregation of networks regarding comparing between regarding the PLV method. So we can see which method is more related to which kind of network or which specific network. And this is, I think that this is the idea that you have in mind to apply this kind of technique. So one important point is that because we have different components, it's also easy to come with those components and to do a clustering method within those components. We know that those components are the component of the compromise, so we can use them, a few components to do the classification and extracting some clusters of the from the data set. Clusters in the case of connectivity means networks. Okay, so I think that I'm going to stop here because I think I give you the big idea of the guys at the level of the variables expert, then goes with compromise within the individuals. This is what we are dealing with. And when we extract those two, the data set, so we come with the data set and we represent the initial data set within this space of compromise. This is why you see experts are represented 6 times because they have 6 components. So we represent them within this space. And we can see how the expert, how the individual data set are related to the different compromise. And probably there are some differences between the different data table over time, if it's over time, or over space, if it's over space. If you are interested by how we can apply this kind of technique, I think that a few years ago, I did some work with oh yes, it's this one, it's in 2003. So this is in a group data analysis, functional MRI. It has been done by Kirif. You know Kirif? Yeah. I think he is now working with Frakowiak in Switzerland. And he was a PhD in my lab. A common PhD with Jean-Baptiste Pauline. Jean-Baptiste Pauline is now at the MNI. Okay, this is like I'm going to share this representation with you. Okay, any question or comment? Just to give you an overview with an example.
It's very interesting. It's just that you have different other methods. I heard about partial least square or other technique, which is not exactly the same topic, but it's a little bit because what we have been doing, for instance, in the lab is you can have connectivity, for instance, let's say you have connectivity in fMRI, in PET and DTI, for instance, and so we have been using partial least square to kind of exploring the data. So what are the underlying hypotheses in going to this approach or another approach?
So this approach, as you can see, is a kind of really a generalization of the PCA technique. It's a
Right, so
complete, it's PCA at high level. So that's all. But at the same time, we can compare this technique to more a technique like a canonical analysis. Canonical analysis look also at the similarities between different data tables. What the canonical analysis did, and partial least square also technique did, is to look at the compromise and derive the first step of this technique, like having the between the expert and having the representation within this space between the expert, and that's it. So if you ask the partial least square to give you some, okay, what about the individuals within this space? The method is not applicable. Okay. And second, if I want now to represent the data set from data set one, expert 2, expert 3, the data set within this compromise, the method does not give you this. So I think that the STATIS technique is a more complete method who can deal with all those questions at once, because you can have all the representation on one representation only.
So,
yeah.
On another topic, so have you tried to apply that when grading students, when we have multiple teachers, grading the student work? Because it seems it would be a great application to look at how different teachers are grading the.
This is done. This
Okay.
has been done several times, and yes, but I have never tried to look at the difference between the student in my class and how you grade them and I grade them, and the reason is probably I am grading at this level and he is grading at that level, and I have some trouble at the end. So this is the only things that, yes, but this is completely a method that we can apply offshore. Yeah. Okay, so if you are interested, or maybe you in the future you are interested by applying this technique, the beauty is that my colleague Hervé Abdi wrote a very easy program to use in R. You have just to prepare your data set and then click, and you got everything to do the analysis easily. So so I can send you the link that you can you can play with this technique. Arsalan.
What you mentioned is limited to linear similarity. Is there any non-linear extension of this method?
Oh, yes, Abdi did something very interesting because sometimes from the data set that we have, we can have the data set X, I mean, as I mentioned, or we can have the connectivity matrices, things like that. And we can try to associate an operator. For instance, if you have covariance matrix, if you have like, this is your data set, what is the operator who is linked that you are going to diagonalize? And we did this work in our team with Obai and another student, where we see that the connectivity matrices, we need to link the Laplacian operator, who play the role of the covariance matrix. X, covariance matrix of X, connectivity matrix, Laplacian operator. associated to this one. So anyway, just to say that, but still we are in a linear decomposition problem. And what Hervé did is, if you have now similarities between individuals or variables, and now what is the operator that you are trying to deal with? And he comes with a generalization of STATIS. He call it d-STATIS for dissimilarities, STATIS dissimilarities. And in this case, we can deal with a non-linearity between variables because this is included in the dissimilarity itself. Then the method itself at the end is a linear method, but it decomposes something who is non-linear within the data set.